Welcome, ladies and gentlemen, to our joint REFLECT and GEOPRO webinar on predictive modeling for applications in geothermal. My name is Katrin Kieling and I'm working at the Helmholtz Centre Potsdam, GFZ, the German Research Center for Geosciences, and I'm the project manager of the REFLECT project, which is a Horizon 2020 project on redefining geothermal fluid properties at extreme conditions to optimize future geothermal energy extraction. In the REFLECT project, I have the pleasure to work along a number of outstanding researchers from 10 different European countries who are committed to close gaps in the database and in the basic understanding of chemical and physical properties of geothermal fluids. And with that, to prevent unwanted processes during geothermal operation so that they can be avoided by an adaptation of the operation or the plant layout. Today, we will focus on the work on predictive modeling performed within the REFLECT project. And this includes, on the one hand, the modeling of chemical processes in the subsurface, the geothermal well, and on the other hand, also processes that are taking place above ground in the geothermal installations. Since this topic of predictive modeling is also in the focus of the GEOPRO project, which is another European project funded under the same call, it only made sense to have this today as a joint webinar with the GEOPRO project. And I now have the pleasure to welcome our three speakers to this webinar. We will start with a presentation of the coordinator of REFLECT, Simona Regenspurg from GFZ Potsdam, who will give a short introduction to the REFLECT project in general. And this will then be followed by a presentation by Laurent André from the French Geological Survey, BRGM, on reactive transport modeling with application to geothermal wells. After that, we will have Pejman Shoeibi Omrani from the Netherlands Organization for Applied Scientific Research, TNO, who will present his modeling approach for calculating the impact of geochemical uncertainties on scaling precipitation and geothermal assets. And finally, our GEOPRO project partner, Per Kjellgren from FlowPhys will close the webinar with presenting the geothermal flow assurance simulator. Each of the presentations will be followed by a 5 to 10 minutes question and answer session. And for that, I would also ask you right now to type your questions into the chat, and I will then read them out loud to the presenters, and you can type the questions already during the presentation such that we can then directly attend to them after the presentation. And a very last remark before we really start, the webinar will be recorded, and my colleagues, Maria Lopez and Anita Stein from the European Federation of Geologists, they have organized this webinar, and they will also afterwards share the recording on YouTube. Having said that, we will now start with the first presentation, and I'm happy to present Simona Regenspurg. Simona Regenspurg is working as a research associate at the Helmholtz Centre Potsdam, German Research Center for Geosciences in the section Geoenergy since 2009. Simona studied geology and hydrogeology at the Ludwig Maximilians University in Munich, Germany, and currently she's the head of the working group Geothermal Fluids in the Geoenergy section of GFZ. The focus of her research is on study of geochemical processes that take place during the operation of geothermal plants, and because of that, she's also the coordinator of the REFLECT project and the scientific head of this project. And with that, I hand over Simona. The floor is yours.
Thank you, Katrin, and welcome also from my side to our webinar. And this time we want to talk about the predictive modeling for geothermal. As Katrin said, it's a joint project together with joint webinar together with the GEOPRO project, sort of sister project that was also funded the same EU call as was the REFLECT project. I will give you now a short introduction about the REFLECT project, and later on you will hear then about the aspects of the GEOPRO that are sort of related to REFLECT. REFLECT stands for redefining geothermal fluid properties at extreme conditions to optimize future geothermal energy extraction, and it answers the call, the European Union Horizon 2020 call on optimizing manufacturing and system operation. REFLECT started on the 1st of January 2020. It goes for 3 years and it's coordinated by us at GFZ Potsdam. And yes, since it's almost over now, the project, so we have another half a year of project duration, we until now have already quite some results together. We are a group of nearly 20 partners from science, industry, and geological surveys around Europe. You see the map here and the logos of all our partner institutes. And yes, so with that, I'm coming to the background of the REFLECT project. The problem that many geothermal operators encounters are in terms of chemistry, scaling and corrosion that occur in geothermal plants or in geothermal systems because of reactions of the geothermal fluids with the surrounding water or due to changes in pressure and temperature. And these reactions, they are very difficult to predict because many of the properties of the fluid and the reactions are very difficult to predict. And in the end, it comes to scaling and corrosion. You see here a couple of very nasty examples of that. And that causes downtime, high maintenance costs, and even failure of the geothermal installations. And in order to understand these reactions better, we developed the REFLECT project. And these properties that are not well understood, the goal of REFLECT is to get a better understanding here. And I show you now just in terms of temperature and salinity, how geothermal fluids basically look like and what are the unknown properties of the fluid. So you see in this diagram here, temperature salinity diagram, and most of the fluids of geothermal fluids, I'm talking here mainly about temperatures above 100 degrees C, are either of very high temperature and low salinity, this is what we call type A fluid, or they are of extremely high salinity, so going up to 450 grams per liter salt content, but then of lower temperature, like just maximum of 200 degrees C. So these are the ranges of geothermal fluid that you can find in most of geothermal systems. And in the dashed areas, you see the fluid properties that are not well understood, but investigated in the REFLECT project. And these are information about gas solubility, like in orange, or mineral solubilities. In general, that's what you find in the purple area. Silica precipitation is a very big issue, especially in the high temperature geothermal fluids. This is the blue area where silica precipitation mainly happens. And then we also have some properties that are hardly investigated at all, and this is microbiology and the organic content of geothermal fluid, which mainly occurs at the, let's say, lower temperatures up to 150 or 200 degrees C, where you can still find some traces of microbiology, and these impacts are also investigated in the REFLECT project. And with this general overview, just a remark on the main objective with that. What we want to do in REFLECT is to do accurate predictions by a thorough knowledge of the chemical and physical properties of the geothermal fluids. And the concept of REACT is therefore to react instead of to move from REACT to REFLECT. So the aim of REFLECT is to avoid the problems related to fluid chemistry rather than just to treat them. And the avoiding goals that one has an understanding and can do the right predictions of the chemical reactions. We have 7 goals in REFLECT that are mirrored in the structure of the project. You see the structure of the project on the right-hand side and the 7 main goals on the left-hand side. So one of the, or actually the major goal of REFLECT is to extend databases for mineral precipitation or fluid properties to higher temperatures and higher salinities by lab experiments and also by modeling. And that we do in both work packages 1 and 2 for the high temperature fluid and for the very high salinity fluids. That means characterization of fluids and also complexation and precipitation to simulate complexation and precipitation reactions. The second goal is to determine the extent and location of the degasification front of geothermal fluids, or to determine the when and where gas bubbles basically form in a geothermal system. And here we look also at both at the high temperature and the high salinity fluids. We also determine type of organic matter and microorganisms. This is more for the high salinity fluids because at the very high temperatures, organic matter and microorganisms do not occur or play a very, very minor role. And then we look at the fluid physical properties at various temperatures, pressures, and salinity. We also aim to develop a downhole sampling technique for hot and super hot systems. And then we have 2 goals that are that go more into the data application, while the goals 1 to 4 deal mainly with the data generation. The data application is first that we want to develop a fluid atlas that shows fluid properties across Europe for different geological formations in a sort of fluid atlas, a digital fluid atlas. Here we had a webinar the last time, like about a month ago here. And this time, today, we want to talk about the system modeling. So the goal is to do verification of the data set that we obtained in REFLECT by application in reactive transport modeling. And that's where the webinar goes today. Just a few words about the model input data. These can be the properties of, or have to be the properties of natural geothermal fluids. These properties are also collected in REFLECT at various geothermal sites. So we have a couple of high salinity sites as marked green here, some high temperature sites as marked red, and some high salinity and high temperature sites in orange. So these Insheim, Tuzla, and Aydin are both high saline and high temperature sites. So these are properties that are measured within REFLECT. So we do measure like basically all properties that are possible, and they should also, of course, in the end go into the models. These are physicochemical parameters, cations, anions, the gases in there, and also to see and investigate what sort of scales form at the different geothermal sites in terms of chemical composition and mineralogy. And we measure, of course, also organics, microorganisms, and several isotopes at these sites. But these parameters so far do not really go into the geothermal model application. Besides the properties of the fluid, then what we also do in REFLECT is to perform experiments to extend the databases of the geochemical reactions that go into the modeling. And the different experiments that we perform are on gas solubility, on mineral solubility, and also on kinetic data. And we investigate them in REFLECT with respect or to determine the effects of salinity, temperature, pressure, or metal impurities, and of course also organics and microbiology that we investigate, but that, as I said, do not so much go into the actual modeling. And just to give you 2 examples in the end, how these data are generated, for example, to determine solubility of amorphous silica, we have different methods, different laboratory setups where this is investigated. For example, here in a setting from Juliane Kummerow at GFZ, where she's investigating by measuring the impedance spectroscopy the silica solubility. So she has, for example, here an autoclaves that can be, where the temperature can be adjusted up to a couple of 100 degrees C, and high pressures, and she does measuring on silica solubility. Or on the right-hand side, you see a similar setup, but here you have the autoclave within an oven, actually, where that can be heated up. And here the silica solubility is investigated at different salinities. See, with increasing temperature and change of salinity, you get different silica solubilities. This is just an example. We have a lot of these experimental setups and many groups that investigated. But this is topic of the next webinar, actually, that we will have in about a month ago, And just another example of what we do in terms of experimental investigations is to determine the effect of salinity, pressure, and temperature on the gas solubility, or also to determine the effect of gas bubbles on rock permeability. This is done at the Technical University of Delft. Here you see a setup of Chris Boyji, where he uses a visual cell and a high-speed camera to monitor the occurrence, the size, and the kinetic of gas bubble formation, and this will then put into solubility models. This is again an example of how the laboratory experiments on the data can then go into a modeling approach. With this, I'm coming to the end of my presentations. As I said, this is number 4 of our webinars. They all can be found on YouTube. So we had a webinar on the geothermal operation at Insheim, and one on geothermal energy in Turkey. Last time we talked about the geothermal fluid atlas, and today about the predictive modeling. And next time will come our final webinar on experimental results and REFLECT. So then you will learn more about all the different experimental setups and see some highlights from these results. And if you want to see us live and in color, you can also go to our session at the EGC, European Geothermal Congress in Berlin in October 2020. For more information, visit our website or go to our sites at Twitter and LinkedIn. With that, I thank you for your attention and give the word to Katrin again.
Thanks a lot, Simona. Thanks for the introduction to the REFLECT project, and also for providing a bit of context how the predictive modeling is integrated along with the other parts of the project. And now I will directly start with the presentations on the modeling. So first, our REFLECT partner, Laurent André, will present reactive transport modeling with the Coupled OpenFOAM PHREEQC platform application to chemical reactivity in geothermal wells. And I shortly introduce Laurent. Laurent André is working as a research engineer in geochemical modeling at BRGM, the French Geological Survey, since 2006. His research focuses on the study of water, rock, gas interaction within deep reservoirs. Laurent obtained his PhD in geochemistry at the Montaigne University in Bordeaux, France, and has completed 2 postdoctoral research fellowships at IFP Énergie Nouvelle and Neuchâtel University in Switzerland. In the framework of the Horizon 2020 project REFLECT, he mainly works on the reactivity of fluids in the geothermal loop, including injection and production wells, and also the surface facilities. And with that, I welcome Laurent, and I'm curious to learn more about the reactive transport modeling.
Thank you, Katrin, for this introduction. Good afternoon to everyone. So during this short talk, I will present you some of the numerical developments performed in the REFLECT project. So in order to build a new coupled code for reactive transport modeling. And I will present you some application of this code to study the chemical reactivity in geothermal systems. So before starting, I want to acknowledge my co-authors, so from the University of Orléans and also from BRGM, for their contribution for this presentation, and also for their contribution to this work. First, as everyone knows, the geothermal fluids are very often hot, saline, and corrosive. And of course, their exploitation can raise severe impacts on the different parts of the geothermal loop. Simona already presented some pictures. You have here other pictures of corrosion and about scaling inside the tubing and inside the well. So of course, you can see that we can have important damages which increase the maintenance works and costs. So it is therefore essential to have a robust and adequate numerical tools able to predict the chemical phenomena in order to anticipate them and also to treat the fluids before they occur. So it is one of the objectives of the REFLECT project. It is to be able to develop a code, a numerical code able to predict the behavior and the chemical behavior of the fluid inside the production, the geothermal loop. So I mean in the production and in the injection well, but also in the heat exchanger at the surface. And of course, we need to take into account all the modifications of the exploitation conditions, like, for example, the variation of pressure, temperature, and salinity. And we have to determine what is the impact of this pressure, temperature, and salinity conditions on the chemical reactivity. Especially, for example, some phenomena like degassing, pH changes, and potential mineral precipitation. So we really need to, and it was one of the challenges, it was to develop and to include all these phenomena in a single code. So what we choose as a methodology, it is to use two open source codes, which are highly popular in their respective communities. So on one side, we use for modeling the dynamic of the fluid inside the tubing, we decided to use the OpenFOAM code. So it is able to take into account the characteristics of the tubing, like of course the length of the well, but also the diameter. It is able to take into account the exploitation conditions with the possibility to calculate flow rate, pressure and temperature profile, but also to take into account the physical properties of the fluids. I mean the gaseous and the liquid phase. So we need to integrate the density and the viscosity of the different phases. So it is OpenFOAM for the dynamic part and for the transport, and for the chemistry. So we decided to use FLOPhys, which is a well-known code for calculating and modeling the chemical reactivity of the fluid. So, of course, this fluid integrates the characteristic of the fluid, like the chemical composition. So both of the liquid phase and also the gaseous phase, but also we can work on the mineral solubility. And we can include some constraints about the kinetics or the equilibrium of the system. So, these two codes, so OpenFOAM and FLOPhys, are coupled inside a single code porous media for foam. So the objective, of course, it is to use two open source code and to create a new code which is also in open source. At the beginning, this code was developed to deal with one-phase isothermal and incompressible systems. So the idea was to simulate the transport and the geochemistry in one-phase systems. So I just give you here two examples of some example deal with the code. The first one on your left, on the left here, it is the dissolution of a calcite grain. So this calcite grain is inside a channel. So you have a flow of an acidic fluid from the left to the right, and you can follow the evolution of the size and of the shape of the grain according to time, so at 3 different times. And we can observe both the dissolution of calcite on the left of the grain, and due to the flow, we observe also some precipitation here at the right of the grain. So this is mainly due to the flow. So we can observe the reactivity at the pore scale. We can work also, for example, you have another example here. So it is a fluid which is flowing in a fracture, and we are studying the variation of the mineral assemblage around the fracture. And for example, we observe here the dissolution of celestite and the precipitation of barite inside in the wall of the fracture. So of course this code exists, but in the REFLECT project we go further, because the objective was to work on geothermal systems. So we implemented some options, like, for example, the multi-phase and multi-component reactive transport. We also implemented energy equation to extract, in particular, the temperature profiles. And we included inertial effects and compressibility of fluids. And we started to apply to real-life applications. So as you understand, the code is not only devoted to geothermal systems, it is also useful for other porous media or fracture media. So because we integrated the multi-phase reactive transport, we needed also to implement some models to deal with unsaturated media. So we, of course, introduced some options of relative permeability, and capillarity. And with this implementation, then we can work on more larger systems. Probably, so I don't describe in detail this topic, but about the multiphase flow and the resolution of this multiphase flow. So, of course, there exists different ways to solve this multiphase flow. So what we choose in our approach, it is to use a separated flow model. It means that we are solving equations for both the gaseous and the liquid phase. So of course, we are considering some interactions between the two phases. You can dissolve a liquid in the gas and the inverse also, but we have a separate equation for both of the gaseous and liquid phase. Concerning the coupling between and the procedure of coupling between the flow and the chemistry. So we decided to use a sequential approach. So it means that all the pressure, saturation, and velocity equation are solved by OpenFOAM. And then from this data, we can determine and we can solve the transport equations, both for the different phases, so for the gaseous and the liquid phase, of course. So when the transport is done, then we are moving to the chemistry. And in this case, so of course, it is FLOPhys, which is solving all the chemical equations. So we can run the chemistry according to equilibrium or according to kinetics constraints. We have also an update of the chemistry of the chemical composition of the different phases, of gaseous and liquid. We are also an update of the saturation, which is given according to the saturation, the partial pressure of the different gases. And we have also an update on the temperature. And then, of course, we are this new saturation are sent to OpenFOAM to update the saturation and compute the mobility terms. And of course, when all these calculations are finished, we are moving to the beginning and we are starting a new time step. So this code, so Porous Media for Foam, has been was benchmarked with other codes, with other reactive transport codes. So I show you previously 2 examples about reactive transport at the pore scale, about reactive transport in a hybrid setup with a fracture and porous medium. And so now we are working on the multiphase system and with an application to geothermal systems. This is what I want to show you now. Of course, so as I said you at the beginning, we have the possibility to work on different geometries. So it depends, for example, if the well is has a constant diameter, or we can work in 2D geometries with different subsections and different diameters. So I will show you today just one example, an application case to a real case. So it is a well from one of our Turkish partners in the REFLECT project. So the total depth of the well is 540 meters, and we have 3 different sections. You have here the different the characteristics of the well with different diameters, and you have here the mesh that we built with a refinement close to the junction. It is just to catch the different phenomena that can occur at this junction. And what we observe, it is, of course, we can calculate the variation of the pressure. So you have here a pressure profile inside the well. We can calculate also the velocity inside the well. Of course, it is varying according to the diameter of the well, but we can also calculate the evolution of the chemistry. So here it is just a test case. So we are just pumping, exploiting a fluid which is in equilibrium with the reservoir. So it is in equilibrium with quartz. It is oversaturated with calcite and undersaturated according to dolomite. And so the saturation index is varying according to the profile of temperature and according to the temperature and pressure profile. Just one more concerning the junction between section 1 and 2. So it is one of the specificity of this code. It is that we are able to simulate, because by using some Navier-Stokes equations, we are able to catch some phenomenon in specific places of the well. And for example, what we observe, we have here the flow line in the well, but in the corner here, we observe some vortices. So it is specific flows, and we suspect that the specific flows can involve some specific reactivity in this locations. So it is one thing on which we are working. So just to conclude, so we have now a new code, a new open source code that we can use to different applications. in multi-scale, multi-phase, multi-compositional and multi-dimensional systems. Of course, we plug this code with FREEQC to calculate the chemical reactivity, but of course you can change the package if you want. So we apply it to different models, and we are now using it for geothermal systems. So this, you can find some information on this code. So you have, for example, a user guide, which corresponds to one of the deliverables of the REFLECT project. You have some reports, you have a brochure, and you have here some information on the code. So of course you can download it because it is available on GitHub. So you can download the code, and it's free. You have some papers, and we will also attend the next EJEC conference in Berlin in next October. So of course we can continue to discuss on this during this meeting for the people who are attending it. So thank you for your attention, and of course if you have any questions, feel free to ask.
Yeah, thank you very much, Laurent, for the presentation of your work. Again, if anyone has questions, please type them into the chat or into the Q&A tool. We have one question already, but I think it has been answered in the talk. The talk was asked very early. Concerning the OpenFOAM plus FREEQC coupling, can the coupling be used in multi-phase flows? And is the coupling limited to any specific solver in OpenFOAM? Maybe you can just repeat.
Thank you. Yeah. Yes, what we tried is to use the OpenFOAM, yes, to work with multi-phase flow. So the objective is, for example, for geothermal application, it is really to work on the gaseous and on the liquid phase. So yes, of course, the coupling. So I don't show here the first results that we have on these developments, but yes, the coupling can be used for multi-phase flow. And about the second question about the solver, you have many possibilities, many options that are included in OpenFOAM. So of course you can change your solver if needed.
And there was also a follow-up question on this one. Does the code on GitHub include the multi-phase flows?
I think not yet. Because we are finishing the last developments, and of course we want to benchmark this part with other codes. So no, not yet on GitHub. There is just the one phase system for now, but we plan to release the new code in the next month.
Okay, thanks a lot. Then there's one question: will the slide be available after the awards for download? And I can answer that already. Yes, we will make those slides available on the website for download after the webinar. And maybe one more question, because it was, well, at the beginning, someone asked a very complicated question on what else we all need to take into consideration, but they also wrote about the processes in the reservoir. So can the processes in the reservoir will also be modeled? For example, if we now have these ATIS reservoirs where the temperature is changing by the influx or something like that, can you also model this with your approach?
Yeah, so yes, it's not the main purpose of the REFLECT project, because in the REFLECT project we wanted to focus on the geothermal loop, so the injection, production well, and surface facilities. So we are not calculating or simulating what happened in the reservoir. But yes, the objective of porous media for foam is to work on very different systems For example, yes, in a well, but also in porous media, in fracture media. And of course, yes, we can use now the code to work at the reservoir scale. So it is really a multi-scale code. So you can work at the pore scale, so at the very small scale, but you have also the possibility to work at the larger scale, like in the reservoir.
Okay, thanks a lot, Laurent. And I think at this point, we will move on to the next presentation. I would like to move now forward to the presentation by Pejman Shoeibi Omrani. Pejman holds a master degree from the Delft University of Technology in Sustainable Process and Energy Technology and a minor in Applied Mathematics. He's a senior scientist at TNO, focusing on production optimization and digitalization of the geoenergy production systems. And this includes, of course, also geothermal energy. He has been a scientific lead of several national and European projects on the topic of geothermal production and flow assurance. And in addition, he is leading several projects on deploying artificial intelligence technologies in the energy sector. And this answers already one of the questions in the chat. Today, Pejman will give a presentation on the impact of geochemical uncertainties on scaling precipitation in geothermal assets. And I'm now happy to hand over to Pejman.
Thank you very much, Katrin. So good day, everyone. Let me first share my screen. Thanks a lot for this opportunity, and also all of you who are attending our webinar. So today I'm going to talk about a part of the activities we do within the REFLECT project, which is about quantifying the impact of geochemical uncertainties. Specifically, we are looking into the scaling mechanisms in the geothermal systems. And this is something that will be evident at the end of the presentation, that this sort of the workflow can actually be applied to various operational challenges in the geothermal systems. So it's not going to be limited on the scaling scaling problem in the geothermal systems. This work is has been done together with several colleagues of mine that I have to also thank them for their contribution to the work. And in terms of the importance of the work, why do we do this, is, as it has been already said in the past two presentations, the operational challenges in geothermal systems, things like scaling, corrosion, erosion, pump failures, these are the things which are the biggest headache for the operators. And if the operators are unable to forecast these sort of issues in advance, and knowing what will be the impact of various mitigation measures on, for instance, the precipitation in some critical components like heat exchanger, or for instance, clogging of the filters, then in that way, they can actually optimize their process and start to be more proactive about the operation rather than staying reactive. So the whole goal is about making good forecasting model, and to make the world good, a bit more specific, I mean, accurate and robust prediction models. And if we're looking into the, for instance, the scaling corrosion issues, these sort of problems are a combination of what actually is being produced, your brine composition, at which conditions this brine is being produced, so mainly what sort of pressure and temperature would you see in the whole system, and at which point you might have a potential to get these sort of issues. And also the whole interaction that you have between your chemical reactions and the hydrodynamics of the flow. So depending on what sort of turbulent flows and what sort of shear rates, flow rates you would expect in the system, the whole problem can change. So you would see that there are three components playing a role over here. And within this project, we wanted to bring them all together to make it accurate, to make it more representative. But also we have another word, and that's robust. And we know that this is also an important factor within the predictive models. But why is it important? So in a lot of projects, we are developing models, but I would like to always emphasize that we are living in the world of uncertainties. So as one of the great statisticians of this century said, is that all models are wrong, but some are useful. So it's good to know that all the things we're developing are wrong, but how we can make it useful. And that's going to be the part that I'm going to hopefully give some insights about why is it important to take into account the impact of the uncertainties. So not to get too disappointed by the fact that whatever we do is wrong. So let's say, often what we have is we have a computer model, you have a simulation code, you give it some properties of the, for instance, fluid that you want to model, you give it some initial condition, you give it some boundary condition, and then you get a single output. So a single input, single output. That's a deterministic word that we use to live with it. But how about the fact that also the input to this model can be uncertain? It can be not, that's when you start to go in the non-deterministic world. So the input of the model is uncertain. You propagate this into your computer model and your output will also be uncertain. So this is one aspect which is very important. And if you look inside our computer model and solver, there would also be a lot of uncertainties associated inside the model. And these are the two different types of uncertainties that we are dealing with it. If we want to make it a little bit more formal, we have two types of uncertainties called epistemic and aleatory. Epistemics are the ones that we often say these are due to the lack of knowledge. So you can reduce these uncertainties. So if you say, this is my current state of the knowledge and this is the certainty that I would like to approach to this, there is a part associated with epistemic uncertainty that when you get more knowledge about your process, you can reduce this. So this, you can say somehow it's represented in the model. So model uncertainty is the part that if you make your model more and more accurate, then by that also you're reducing the errors and uncertainty in the system. But there is a part that often is due to the inherent uncertainties within a certain process. It could be a randomness or a, let's say, certain process that you can't get information and knowledge on that. And this is going to be an aleatory uncertainty. So from a certain point, when we get into the what they call it the perfect state of the knowledge, you can't do better than that because there will be a lot of variations and random noises in the system that you can't change this. To make this a little bit more sensible, aleatory uncertainty, we often call it as an input parameter uncertainty. Yeah. So within REFLECT project, we mainly focus on the aleatory uncertainty. And why is it important? Imagine we want to predict the scaling in our system. What do we need? We need to have a very good description of the fluid composition. The way that we sample the fluid from the system, where do we sample, which method we use for sampling, depending on what's happening in the system, upstream of the point that you're sampling, if there has been some corrosion or some scaling, or if some inhibitors are being injected, that's going to impact the quality of your sampling, and most importantly, also how you're going to analyze the samples. So all these three are going to add to your uncertainties. There are parts that you can actually reduce, but eventually you can't run, let's say, a 10,000 sampling campaign to make sure that you have a great description of the fluid. So you have to live with part of these uncertainties, and we would like to use tools to quantify this uncertainty. How big could it be, and what's the impact of this uncertainty in the end in, let's say, for instance, a prediction that you want to do in terms of the scaling in the system. So in order to make an accurate and robust model, what we did, very similar to the previous presentation by my colleague from BRGM, Laurent, is we are also coupling models. We are also coupling the hydrodynamic models with chemical models. And in this case, we have used a reflux model to model the multiphase flow in the system. And this is type of a model which are very good for modeling the flow in the pipelines, multiphase flow in the pipelines. The reason for selecting this model, because it's a 1D dynamic model. So if there are some transient in the system, these models can, up to a good extent, capture that. And most importantly is that it's 1D. Especially if you want to look in using these models in the real-time aspects, in an operational time scales, these will be very suitable models that you can use. And this reflux model will tell you something about the flow properties. And we couple this with FREEQC, which is the chemical reaction model, and this can estimate, let's say, all the kinetics with respect to your mineral precipitation. So how the workflow works is that you provide some inputs, which are the water composition, piping materials, and the conditions of your system in terms of, for instance, well pressure, temperatures. Well, it depends on where you're fixing the system so that you can define as a boundary condition. Based on the water composition, we are having two sets of models, which one will tell you something about the vapor liquid equilibrium, and one will tell you something about the scaling kinetics in the systems and the scaling potential and how much amount you can expect in certain pressure temperature conditions. The hydraulic model will be solved that at each point in the system you can estimate pressure, temperature, and the fractions. This will be fed into the FreeQC model to tell you whether you would expect at this point any scaling to occur or not. And if you expect any scaling to occur, we have an extra precipitation model, which will say, okay, at this point, you would expect X grams of this material to be deposited. This would fed into an additional model, which is a roughness model, because over time, when you get more and more precipitation at a certain location, then this would start to build up, and that would impact the additional resistance that the flow will see. And this roughness model will be updated in the next time step that you're solving your drift flux model. So you would couple the flow, let's say, properties to the FreeQC to couple it with the scaling. The scaling will add something into the resistance of the system, and then in the next time step, you would resolve the flow properties with the new roughness and resistance scheme. So in this way, you can actually solve the whole system. This composition of the fluid, it's really the heart of the whole workflow, and this is the part that we're going to look into. If you have an uncertainty in this water composition, how this would actually propagate in the whole system. Maybe you are here 5% unsure about your water composition, and eventually it means that you're going to be 40% unsure about your flow rates, or it's going to be the other way around. And that's the, let's say, the puzzle that we're going to show at the end of this presentation, what sort of insights we got from this workflow. As a case study, we take a very simplified heat exchanger model. So simply a piece of pipe where you're exchanging heat based on a certain heat flux. So that means that for the different flow rates and with different heat demands, you can solve for the pressure and temperature that you would expect at the inlet and outlet of your system. And we wanted to look into the impact of composition uncertainties. So there has been some fluid database where we look into the ranges of the uncertainties that you would expect from samples that you get from one well or samples that you might get from multiple wells within the same formation. And based on this, we get some, let's say, expert judgment about which components has the highest uncertainty and what will be the level of that uncertainty. So here, for instance, for these samples that we took from a slough formation in the Netherlands, we see, for instance, iron, nickel, aluminium, they have very high uncertainties, when we have to see if these sort of uncertainties have any impact on the output that we want to predict. Use different strategies for sampling an uncertainty, let's say, parametric space. These are not very expensive simulations. If you go to expensive simulation where doing all this realization becomes very expensive, it's best to use other type of methods. But for now, we use different type of sampling and a very simple Monte Carlo propagation in order to estimate the impact of fluid composition uncertainty on the quantity of interest. I will take you through the 3 examples very quickly, just to give a bit of a flavor of what you can get from this sort of workflow. And first, I start by this part of the workflow. So just looking into the impact of the water composition uncertainty on the scaling potential that you would expect from your chemical model. We run one case with a focus on the barite precipitation. And for now, just a single pressure and the temperature, and we purely look into the water composition uncertainty, which we got it from multiple samples from a single well or multiple samples from multiple wells from the same reservoirs. And well, nothing spectacular. Of course, what you see is that if you go to multiple samples from multiple wells, because of the variation that you expect from the different wells, your uncertainty bounds starts to get larger and larger. And what we could also see within this is that the barite precipitation is of interest, and we have several parameters with their own uncertainties. What we could do with this sort of tools, we could also see which of the parameters are actually causing the most significant impact on the output. So in the case of a barite precipitation, what we see in this case, which is called the Sobol analysis, where we look into the, for instance, the variations from a single well, we see that in this case, let's say the sulfur and barium has the highest impact on the let's say the uncertainties that you see in the barite precipitations in the system. Similar thing as well, if you see into the formation variations, the order of the parameters has changed, but these are also always good to do to make sure that, well, actually the observations that you see, does it make sense or not? The second part where we test this workflow is actually when we looked into the impact of the uncertainties coupled with the flow model. In this case, we also look into the flow in the heat exchanger and then see how do we expect the uncertainties of a barite precipitation in a heat exchanger. So you can see a pressure temperature profiles within this heat exchanger that you get a temperature drop from roughly 100 degrees to around 40 degrees. And you can, at 5 points which we have picked over here, you can look into the chance of the barite precipitation and how it changes over time. What is very interesting in this case is that if you look into the barite precipitation at along the depth of along the, let's say, length of the heat exchanger, in this case, the nominal point, the single deterministic point that has been used in this simulation, shows that you would expect barite precipitation. This is the line over here with an X amount you would expect this. But if you say, well, what if my brine composition is a little bit different, you would end up with a lot of instances that you will see no barite precipitation. So actually the mean of your distribution is way lower than the single point that you calculate for the barite precipitation. And this can have a big impact on how you're going to decide on a certain operational strategy. Should I now increase the temperature, decrease the temperature? This can have a big impact on that. So it is very important to see, okay, again, a very, well, a fancy tool, a lot of pictures, what I'm going to do with this. And this is, let's say, a way that you can see that if you take into account the uncertainties, it might be that you have a lower chance of precipitation than you originally thought, if you consider your whole uncertainties. Last part is when we take into account the whole thing. So now we want to look into the water composition uncertainties. If you propagate that through your scaling model, couple it to the flow model, create the roughness, and then see over time, if you get the precipitation, how much the production can decline. That's the part that I want to see. And it is important because your flow properties like the turbulence level has big impact on how your roughness, morphology, shape, and the, let's say, size will be. And eventually that's going to be the resistance that your system will see. So in this case, we've created a roughness model based on the, let's say, the force balance between the precipitation and the turbulence levels that you have in the system. And you can actually simulate the roughness buildup in your pipe flow. And when we couple that to the flow, first we look into the impact of this additional layer that you're precipitating in the efficiency of your heat exchanger. So you actually see the heat transfer from your heat exchanger along the tubing and how much is being decreased over 25, 50, 75, and 100 days. So you see that in some places in your heat exchangers where you have the most precipitation occurring, you can get reduction in your heat transfer by 10% after only 100 days. So that can have a big impact on the COP of your system. And when we couple the whole thing to estimate the production decline over the time, we see that, okay, after 100 days, your production on average will be reduced by around, let's say, 5 cube an hour. So not a very significant one in this case. And you can estimate the uncertainties, so also not too sensitive to all these variations that you have found. And another interesting point is that if you consider the uncertainties compared to the deterministic point, which are shown here by red, overall, you would expect a bit of a higher rate because in this case, the precipitation was not as bad as what you thought in your deterministic case. So This is actually a good case to show how things can get a little bit better if you consider uncertainties in your system. And one interesting thing is that on average, when it has been set to have around 5% uncertainties in the brine composition, that led to only 1% uncertainty in the flow rates. So in this case, you might see, well, my brine composition is too uncertain, but when everything comes together, that impact will not be that big. So this sort of workflow would really help you to know that, well, if I have errors or uncertainty somewhere, how this thing is going to propagate in the whole system and how it's going to impact my production. So we've created this automated workflow to perform uncertainty quantification. This can give additional insights in, let's say, the confidence bound that you have in your prediction, and also how much the uncertain parameters are impacting your prediction. The workflow is very generic, so you can also use this if you, for instance, want to estimate corrosion, estimate erosion in your system. The workflow itself is quite generic. It's just a way how you're going to couple to your predictive models to estimate the uncertainties. One step which we still have to look into is that these are all modeling exercise. All models are wrong. So we need some experimental data in order to also estimate the model or epistemic uncertainties. And soon also one of the things that we will do is that we will also put an example on a GitHub and with a link on the REFLECT website on how you can couple uncertainty quantification workflow with the FreeQC model, and eventually you can use that to couple it to any simulator that you are using. So with this, I would like to conclude my presentation. We talked about uncertainties, and this is the best code that I could find to demonstrate the uncertainty by Donald Rumsfeld back in 2002. There are things that, we know, those are known knowns. We also know that there are known unknowns. So there are some things that we do not know, but often there are also unknown unknowns. So these ones are things that we don't know that we don't know. So I hope that I gave you some information about the things that you don't know, or don't know. And I'm happy to take your questions.
Thanks a lot, Pejman. Very interesting talk.
Thank you.
And very nice quotes. And we also have a first question, why the flow model is considered steady, but the other models were unsteady?
You mean the reflux model, to be specific about the question? So the thing is that, yeah, so I can give a generic answer, but then maybe I can follow it up in the chat. The drift flux model, you can use it in the transient condition. That's the whole thing. That you can actually make a dynamic multi-phase model using drift flux. And in this case, indeed, we were only looking into the steady state part. So that's of course a possibility that you can do. We went to the drift flux model because eventually, if you're expecting any dynamics caused by for instance, the multi-phase flow in the system, you don't want to switch too much between the models. So in this case, we were dealing with a single phase brine system. That's something that we mainly see in the Netherlands in the low enthalpy geothermal systems. So there was really no need to go to the transient model. But as soon as you start to have multi-phase flow instabilities and some dynamic behavior, then it's best to go with the transient modeling. I hope I answered the question.
I think so, yes. There was also another question which you actually already answered in the chat, but I'm going to repeat it. With the geochemistry data from geothermal reservoir, can we build a machine learning model to predict scaling and corrosion?
Yes, so indeed, I already referred to this in the chat. So there are some work already. There was some work done in the other project performed, which we are also collaborating with GFZ in that. We were collaborating with GFZ in that project. We started to look a little bit into the relation between the brine composition with the different sites and see if that could give us some hints towards a specific scaling or corrosion issue. It all depends on the data that you have available, because you can have a brine composition that can be estimated from the test. But do you have a scaling problem? Do you have a corrosion problem? How accurate is the label that you put for a scaling and corrosion for their type, and how the system has been operated? There are so many information that if they are not available, then yeah, well, machine learning, it can be a garbage in, garbage out. So it can, if you have a bad model, you can predict it very well, but it has no value in it. So it all depends on the quality of the data which is there. But in terms of relating the brine composition from various sites together, I think we made some very nice step in the POFOAM project.
Okay, thanks. And maybe one last question. Could you also turn your approach around, instead of making an uncertainty quantification, make a kind of sensitivity study to see which uncertainty or which parameter you need to have most certain to get the lowest uncertainty out?
Yes, very good question. So the thing is, so you can actually inverse the problem. It might be a bit of a personal taste. What I like about the uncertainty quantification is that within uncertainty quantification, you already do a sensitivity analysis. If you do a sensitivity analysis, it doesn't mean that you have done an uncertainty quantification. But if you do an uncertainty quantification from your input-output relations that you have, you can do a sensitivity analysis. And what I showed in this Sobol variances, that these two parameters has the biggest contribution to your output, that's already a very good initial step to tell you something about what do you need to take care of in order to make a best prediction. So that is very well possible. And of course, there are like Bayesian approaches where you can even optimize it in a direction that you reduce your uncertainties. But I think that will be a separate webinar on its own.
Okay, well then we already have a topic for next time.
I hope so.
I think with that we leave you, and we are going to switch to the next presentation. Thanks again, Pejman. We will now come to our last presentation by Per Kjellgren on the geothermal flow assurance simulator, which he is developing with his team at FlowPhys. Per Kjellgren is a founder of FlowPhys company and has more than 30 years experience in developing high-performance algorithms and multiphysics scientific software for engineering applications within oil and gas, geothermal, and other sectors. He's the lead developer of a new multi-phase, multi-component dynamic pipe network geothermal flow assurance simulator, and that includes novel geofluid models, thermodynamics, scaling reaction kinetics, and device models. And Per is further developing the simulator in the European project GEOPRO, which is also working on the improved understanding and modeling of geofluid properties. And as Simona said, this is kind of our sister project, and that's why we invited him today to this webinar. And that I hand over to Per. The floor is yours.
Thank you very much for the introduction, and hi to everyone. So I will talk about the geothermal flow assurance simulator. And before I get into that one, I'll mention a little bit about the GEOPRO project. So the GEOPRO project, it has 12 different partners from 7 countries, shown here on the map. And the coordinator of the project is a TWI in the UK, and we also have 3 geothermal power plant operators based in Turkey, Iceland, and Germany. We also have participation from the oil and gas industry through Equinor, and then several research institutes, SME, and universities. So very briefly, the GEOPRO project, it focuses on experimental and computational geochemistry, reservoir modeling, and flow assurance. And of special notice is the development of a unique experimental facility, which is this flow loop. So it's a flow loop specialized for geothermal conditions, which means both single and two-phase flows, and up to very high temperatures, all the way up to 230 degrees. This is very special. There exist lots of different multi-phase flow loops in the world, but they are typically targeting oil and gas industry, and they really do not go that high up in temperatures. So this one is special. So notice, for example, when you look at things like corrosion, for example, shear rates and so on comes in, but also temperature and chemistry is very important, of course. So today you cannot really do those experiments, but with this flow loop, we will be able to do that. It is still not operational. I hope it will become operational sometime during the summer this year. The GeoPro project is scheduled to run until end of October in next year. So the scope. Well, the scope of the GeoPro project, it includes new geofluid models, and especially with focus on high salinity and supercritical conditions, and also reaction kinetics, and as well as suitability for an accuracy and robustness when coupled to different equations of state. And for more information about the general topics of the GeoPro and what different partners are doing, I would like to refer to the GeoPro website, so geoproproject.eu. And you can also find there links to, for example, a webinar, Super Hot Geothermal Resources from Discovery to Utilization, that you also can find on the YouTube. And then the rest of my talk here, I will focus on the part that FlowPhys, my company, is mainly doing in this project, which is the development of a geothermal flow assurance simulator. So first of all, flow assurance, what is it? Well, I'm based in Norway with a background in oil and gas industry. And in the oil and gas industry, with flow assurance, we typically mean dynamic simulations of multi-phase flows in pipe networks. And of course, we use it for design and sizing, but also for operational procedures, so like startup, shutdown, inhibitor injection, pigging, and so on. And we use it to look at also at solid deposits, so hydrate, scale, wax, and also integrity issues like corrosion, erosion, vibrations, fluid acoustics like singing, and other things. The term flow assurance was first coined by Petrobras, and it literally means guarantee of flow. And it's considered a key technology in the oil and gas industry. For example, it won an award as the most significant Norwegian invention since 1980. So that covers pretty much the whole oil age in Norway. So why is flow assurance simulations important in geothermal? And first of all, if we're going to say something about scaling rate, corrosion rate, or other things, we need to have an overview in time and space for everything. You know, fluid compositions and so on, but also everything in the system. And with those kind of simulators, you can, in principle, model the whole power plant as well as production and injection wells. And so with this, of course, we can speed up and improve, optimize design and operation. We can test new technologies that are a little bit more specific for geothermal that doesn't really exist in oil and gas, like thermal energy storage and different kinds of scaling management and so on. Why can we not use the flow assurance simulators that exist today in the oil and gas industry? Simulators like, for example, Schlumberger's Olga or LEDA Flow. Well, first of all, the main thing is that those oil and gas-based simulators, they typically lack geochemistry models that are relevant for geothermal energy, so higher temperature, for example, the different fluid compositions. They often also don't have device models. Well, obviously for thermal energy storage and so on, they typically wouldn't have that. And also one thing that is often overlooked is that those solvers, they are highly nonlinear, and robustness is always an issue when you make those solvers. So they are actually tuned towards a lot of different oil and gas flow fields, and they are tuned for these fields, both in terms of robustness and speed. So if you take those solvers and go straight to a geothermal energy system, you really need to modify it so much and tune it in a different way so that it will really require a separate product. There will be two branches of the solver in that case. And they simply haven't done that kind of investment yet. So because of this, we aim at developing a new geothermal flow assurance simulator. And the overall objective is to make this one practical and easy to use software for geothermal engineers. We have a whole bunch of features already developed, some in prototype, some are really very well developed, and some are more at the starting point. But they are listed here in this list here. So I'm not going to go through all of them, just saying that it's a single and two-phase flow is steady state time dependent, so transient or dynamic, say incompressible, compressible, Newtonian and non-Newtonian, and it's for pipe networks, so not just single pipes. We have different other things here. For example, it also includes structural dynamics, and we can also do fluid structure interaction. For fluid models, we also have different options. For example, the FreeQC software that others have mentioned today. But we also have novel geofluid models that are under development in the GeoPro project, and also looking a lot at reaction kinetics. Device models, a whole library of different device models, so ordinary things like pumps and valves and so on, but also more special things like thermal energy storages, special models for drilling tools, well casing suitable for high temperature fields and other things. Some models for corrosion, erosion, and scaling, and we can also do process controls. We can, in principle, virtually optimize things and see how do we control this in the optimal way. For example, minimize injection of inhibitors and still reach our objectives. So this solver, when I say flow assurance solver, it really is a 1D pipe network solver, but we also, in our company, we have also developed a 3D multi-physics finite element solver. So that's, CFD, it's thermomechanical structures, fluid structure interaction, acoustics, and we also have couplings between these. User interface and so on, I'll talk a little bit more about. We aim to release this software as a freeware by the end of this year. And we're also planning to have some training webinars and workshops during Q1 next year. I should mention that this software is a large undertaking. It's supported by multiple projects as well as our own internal budget. So we have 7 Horizon 2020 projects where this software is partly developed. So SmartRec, GeoCode, GeoDrill, GeoSmart, GeoPro, GeoHex, well, Galaxy. As you can guess from the name, those 5 here with the Geo, they are all geothermal energy projects. We also have Eurostar's ProCase, which is also a geothermal energy project, as well as a project from the Norwegian Research Council. The pictures you see here, they're all examples of some of the simulations. So the fundamentals on the fluid side here, we have finite element based solving of conservation equations, so conservation for mass, momentum, energy, and species. And it should be noted that because it's a network solver, we also need to conserve these things at the pipe junctions, and there are different ways of doing that. We have homogeneous models and drift flux models for two-phase flows, and we can also take a complex fluid compositions, so multi-component flows, and that could be a chemical equilibrium calculations where we typically use FREEQC. And we also have separate transport equations to look at reaction kinetics, and that is especially of interest when we're looking at scaling agents and inhibitor injections. We could, in principle, put in, any number of equations for the component tracking here. But of course, the more equations we have, the slower it gets. We also have non-Newtonian fluids, and that is useful for drilling operations. Fluid properties, constant, semi-empirical. We can take PVT tables for general fluids. We have coupling to the FREEQC RM library for geochemical calculations. And then in the GeoPro project especially, but also a little bit in the GeoSmart project, there are also new models under development for focusing on high salinity and supercritical systems, and also equations of state, more advanced equations of state. We also, and for the structural part, so we also have structural static and dynamics. So that's an ordinary finite element solver for 1D general elements. So that means 6 degrees of freedoms per node. So you can bend and rotate and drag and compress in all directions. This one is also coupled with the flow assurance, the fluid part of the flow assurance solver. So it's a coupled fluid structure and heat transfer. And here we also have things like more advanced ways of calculating added mass and damping for general geometries, where we're also using parts of our 3D code with arbitrarily Lagrangian formulations, fluid structure interaction, and so on, to calculate added mass and damping for general geometries. We also have some model for the drill I'll show later, and so we can simulate drilling operations. Okay, so using this flow assurance simulator, we have a GUI, so we can, we can both use a menu-based GUI. We can build a model, we can generate the mesh, we can run the simulations. We can also use commands on a command line here, but most of all, we can also use input files and macro files. So if we need to loop or if then else or something like that, and also to have it better documented, we also have macro language. Tutorials, user manuals, help function to reach those and other commands. It also exists in a online way, so we can just type help and then the name of a command, and it pops up a help window. We can reach the tutorials and user manuals from there also. We have some special module, for example, and drilling module where we can look at the whole drill string and the wellbore. We could just look at the wellbore or use it as a production and injection well modeler to build up the geometry and the materials in there in an easier way. Here is some example calculations. So we have a very simple example here. So it's just a schematic network problem. So we have inflow here, outflow there. We got 5 parallel pipes, all with different pipe diameters. And then as a result, we typically get profile plots or time history plots. And so you can see here, like, for example, pressure profiles for each pipe, mass flow, erosion, corrosion, temperature, density, saturation indices of whatever you have in your fluid composition. Concentrations for the species where you have chosen to have separate reaction equations. or transport equations that can also include reaction models. Flow speed and also volume fraction. We can also present this as 3D plots through coupling to open source and software, GMesh, as well as a plugin to commercial software answers for post-processing. Models targeting geothermal energy. Well, we have a lot of different models here. I think for the fundamental understanding of the geofluid models, I have mentioned most of them. Yes, we also making a model for cavitation. The rationale for that is that in some power plants where you want to keep the geothermal loop, single phase, liquid phase, you typically need to have a reasonably high pressure, and that costs energy to achieve that pressure. And in some places, you might have degassing, and that can create heavy erosion. We hypothesize that this is related to cavitation, so we are looking at it, and that is also something that we will look at in this geothermal multiphase flow loop. Other things worth special mentioning is a scaling management system. This is for the GeoSmart project. So when you re-inject your geothermal brine, you typically need to keep the temperature fairly high to avoid excessive scaling. So we are trying to make a system there where we take away the scaling products before the re-injection so that we can extract much more of the heat energy. This has a huge financial impact because it can significantly increase the energy production. So the idea here is that extract the energy quickly in the heat exchanger before the scaling really takes place. And then we have the scaling coming afterwards mainly in the scaling reactor and a retention tank. And of course, if you're going to do this and if you're going to simulate it, so we're simulating it, we're also using process control, so we can look at things like, what is the scaling and what kind of inhibitor concentrations, the temperatures do we need? Also the concentrations of the scaling agent itself, so we can inject pure water, for example, to reduce it and so on. But in order to do this, we need to have really good understanding of the reaction kinetics. So for example, we have implemented a reaction kinetics model for silica polymerization developed by University of Iceland that are also part of the project. Other things, coatings. It is possible to reduce cost by using coatings, so using ordinary carbon steel instead of more expensive stainless steel if we have coatings. But if you do this and if you use coatings everywhere, it will be too expensive. So you need to know where to apply the coatings. And that is something that we can predict with this kind of flow assurance simulator, where to put the coatings. Also corrosion erosion scaling models. So in general, we can get some idea about where to look and how often we need to look at how severe it would be. Thermal energy storage, well, that's for improving flexibility. So we have models for that. We have a dual media thermocline model developed by CEA in France, and they are also developing new models for phase change materials and steam and other kinds of water thermal energy storages. Well casings, it can also be done things there to improve flexibility. So in the ProCase project, we're looking at a novel multi-layer casing, and we're putting in models for how to simulate that as well. So with that one, we can also increase flexibility and increase lifespan. Drilling is a very big cost in geothermal projects, especially deep geothermal. So we have a project on that called GeoDrill, where we use novel method of the drilling, where we use a bistable fluidic oscillator, which enable us to use mud-driven, fluid drilling mud driven down the hole hammer tools which is much better to when you go deep and you need to have cuttings up and stabilize the hole and so on. So we also have models for that in the flow assurance simulator. So I think this is my last slide. Yes. So there are lots of things in this, and I'm happy to take questions, and also please feel free to go to the GeoPro project webpage to see more, and also to our homepage, and also feel very free to contact me for more questions. Thank you very much.
Thanks a lot, Per, for this very interesting presentation. Very impressive. What do you aim to do with this tool? It's a lot of different applications. Maybe one first question. You said in the beginning that you are aiming at a tool which is applicable by geothermal engineers. So the main purpose would really be that people are using the software themselves and you just provide some training, or is it also that you provide the calculations for other people for their geothermal science?
Our aim is really for other geothermal engineers at the different operators or consultant engineering companies to be able to use the software. So that's the aim.
Okay.
So that's why we have also spent quite a lot of energy on making the user interface easy and powerful to use.
Yeah. And you showed this network of pipes where you have, you make your calculation for different parts of the pipes. Can you change the properties along those pipes, like for example the temperature and so on, because it will not be constant along the whole pipe network, or it will be different in different sections of the network?
Yes. So the solver is finite element based. So we model each pipe with many finite elements. So we actually have all the properties. So you can put it as many elements if you want. You could have just one element for a pipe, but you could also have thousands of elements. And by doing that, we can also change properties. So like, for example, things like insulation or pipe diameters or wall thickness or whatever we want to do there. Yeah. Mm.
Okay. Actually, when I look at this slide, what got my curiosity was this one plot with a corrosion profile where you have everything very low, and then I think this is one pipe where they all come together again, where it shoots up, or
yeah, it probably gets higher shear rates there. For the corrosion models, we have different ways. One is to use a NORSOC model, but that one is not that suitable for geothermal because it caps at 150 degrees. But we also have a project called a GeoCode, where we have new measurements, both for coated and non-coated pipes. So we can also take, meta models. So if we just take experimental points, or if we take points from for example, a FreeCorp software for corrosion, then we can create a meta model that we can use in this flow assurance simulator, and then we can get corrosion profiles. But yes, it is often in the geothermal community, often when they do corrosion testing, they often use autoclaves, and they call them flow reactors, because there is a small flow in there. But that small flow, it really only, the point of it is really on the chemical side, so that you get a little bit of, a fresh liquid coming in there, right, for the chemical reactions. But it is basically zero flow speed in terms of shear stresses. You don't really have shear stresses there. And if you look at shear stresses, that's actually an important part of any corrosion model. And that is also what you have in the real geothermal power plants. So all those experiments that are done without the shear stresses, they have rooms for improvement. And with this simulator, we actually get that. We get the shear, we get the shear stresses, we get the temperature, we get the chemistry. Then of course you can argue how good are the models, and they can always be better, but at least we have some data points, and we have meta models. So, you know, provide us better data, we can simulate in principle anything. If you don't have data points, we're kind of stuck with a NORSOC model. Yeah.
Okay. If there are no more spontaneous questions, I think we are at the end of our webinar. Thank you once more, Per, for your presentation and answering the questions. And I would also like to thank all the other presenters for coming today and presenting and answering questions. And of course, I also thank our organizers, Anita Stein and Maria Lopez, for setting up this webinar. Again, a short reminder that the webinar is recorded and will be available on YouTube. And I think with that, we are finished for today. We hope to see you back and one of our next webinars, or as Peter said already, during the EGC, where we will be all present. And with that, I wish you a nice afternoon.